Hello everyone, I'm Aldrich, and today I'll be presenting our paper, Unscripted Retargeting, Rich Prediction for Haptic Retargeting in Virtual Reality. Before I dive into this paper, I'll give a brief discussion about the background. Currently, when users are interacting with an object in a virtual environment, the current commercial solution relies on providing touch feedback with vibration or no feedback at all. When users receive inappropriate touch feedback, it will detract from the overall experience. Haptic retargeting is one solution to improve the haptic experience in VR by using real objects to represent multiple virtual objects. One technique of haptic retargeting is incremental body warping. As shown in the video, the technique decouples and manipulates the virtual hand from the real hand gradually to reach spatially separated virtual and physical objects. The current implementation of body warping on its own is mainly explored in a scripted manner, where the users were instructed what to reach. However, a natural reach interaction should support unscripted interaction. There are two current solutions to support unscripted retargeting interaction, one using additional hardware like eye tracking, or requiring user to use head gaze to select a target prior to reach. Inspired by the current problems, we envision retargeting to support unscripted natural interaction in today's VR. We propose a reach-based prediction model that predicts the user's intended target and applies retargeting to the remaining reach once the model reaches a predetermined level of confidence. We conducted a data collection process to collect the user's reaching movement. We then used its knowledge to build a prediction model, which we then evaluated its accuracy and how early it can predict the user's reaches. Finally, we evaluated with simulation to see how unscripted retargeting affects how far a physical counterpart from a virtual object can be. For the data collection, we recruited 12 participants, including one left-handed participant. The task of this study is to reach the 24 targets placed across a tabletop, and we tracked the participants' head and hand movement. There were two instruction types where the users were either informed or not on what to reach. We did this to ensure that we get the user's reaching movement to all the targets, but at the same time confirming whether letting the users freely reach will affect their movement. We did preliminary visualization to better understand the user's reaching behavior. We discovered that different users typically have similar reaching behavior to reach the same target. This is the case for both instruction types, and so we decided to combine both ordered and random reaches to build the prediction model. Additionally, since we only have one left-handed participant, and they reach differently from right-handed participants, we discarded the one left-handed participant data. We then used this reaching data to build the prediction model. We decided to use long short-term memory, a type of neural network that can be trained with past users' reaches to predict the target of future reaches. When training the LSTM network, we need to decide the movement features to use. So we decided to develop two LSTM networks. The first one we call LSTMP, as we train it with only the hand position features, and another variant called LSTMPR, trained with both hand's position and ear rotation. We then evaluated these two models with cross-validation to compare the prediction performance. Here, we show two figures with the model's prediction accuracy and confidence over time throughout the reach. The two figures contain three lines, showing mean in the middle, and the dashed lines are two standard deviations above and below the mean. We also use the green area to indicate the area where we consider as having low error and high confidence, which is equated based on our data collection and results. We discovered that both LSTM networks perform similarly, achieving high accuracy and can predict early. On average, at around 65% of the reach, the user's reach can be accurately predicted with an average error of less than 3.25 centimeters. This accuracy is considered low, as the closest neighboring target center point is 6.5 centimeters away from the real target's center point. This indicates that on average, we can apply retargeting to the last 35% of the movement. We also discovered that the model's confidence of its prediction on average is higher than 85% around this time. This can be used as the predetermined threshold as to when we decide that the prediction is considered as accurate enough. Additionally, we also explored whether the LSTM model can predict new users' reaches that the model wasn't trained on. So we created a new variant of LSTMP called LSTMPO, which is evaluated using the leave one out approach. From the results, we can see that having the data of the same user during the reach in a training set will be beneficial to slightly improve prediction. However, it is not necessary, as the performance between both LSTMP and PO is very similar. We further compared our two variants of LSTMP and PR with other prediction models from the literature, including the nearest neighbor approach, varying angle, and regression. LSTM performs the best in terms of accuracy and ability to do early prediction, followed by the nearest neighbor approach. And when compared to the nearest neighbor approach, at 65% of the reach, the LSTM networks perform approximately 5 times better and can predict 1.22 times earlier. We then use simulation to see how unscripted interaction affected retargeting, as in how far a physical proxy can be from the virtual object in our setup. To do this, we use the proposed range by Zenner and Kruger of how far a hand can be displaced without being detected. We were able to confirm that scripted retargeting has a larger space to place a physical proxy away from the virtual object due to having a farther distance to apply warping. However, in our setup, this translated to only having 2 lesser physical objects to represent the entire 24 virtual objects in our setup. To summarize, our research focused on enabling unscripted interaction with retargeting. We presented the use of LSTM to predict the user's wishes. This approach is beneficial as it works with today's commodity VR devices and does not add additional steps to reaching with retargeting. Initial results are encouraging to keep looking in that direction, as it's able to predict early with high accuracy over previous methods. However, further user evaluations are needed to fully validate the application of LSTM to retargeting's implementation. Thank you.